Welcome to Exploring Computing. Today's video is Bits, Bytes, and Binary, Part 2, or 1 plus 1 equals 1, 0? So in the last lecture, we took a look at binary numbers and why computers use the binary number system. In this lecture, we're going to take a closer look at how binary numbers actually work. Now, I do want to start off by saying we are going to be taking a look at a bit of math here in this particular video, and I don't want people to think that this is what the bulk of this class is going to look like. This is largely the only video in which we're going to be looking at math, but I do think that having a sense of how these binary numbers really work and getting a sense for when you see a binary number, what it actually might represent is going to be pretty useful as things go on. We're going to see that the binary number system pervades computers, and that there are many, many places where the fact that the underlying representation of data in the computer uses these binary numbers is going to leak out into the real world. Let's go ahead and take a look at this. So let's start off by learning how to count. Now, I know that seems like an odd place to start off a lecture at Stanford University, but bear with me. We're going to review how to count in decimal, and this will turn out to be useful when we're trying to understand how counting in binary works. So I'm going to start off with a 0, and I'm going to add 1 to it. And of course, that's going to give us 1. We're going to add 1 to 1, and that will give us 2. We'll add 2 to 1, and that'll give us 3, and so on. And then we'll continue on. We'll get to 8. We'll add 1 to 8. That'll give us 9. We'll add 1 to 9. And that's where things get a little bit dicey because, remember, we're working with the decimal number system. There are only 10 digits, starting with 0, going up to 9. And so what happens when we try and add 1 to 9 is there's no 11th digit. So what happens is we carry the 1 and we reset our 1s to 0 and we end up with 1, 0, or which is of course 10. Now we can continue on. So 10 plus 1 is 11. 11 plus 1 is 12 and so on. Now when we get to 19 plus 1, well, this is similar to what happened with the 9 plus 1. We know that we can't go to 1 some digit greater than 9 because there are only 10 digits, 0 through 9. And so again, we carry the 1 over and we end up with 20. This will continue on. We get 98 plus 1 equals 99. We get 99 plus 1. And again, we have this situation where neither the 10's digits nor the 1's digit can go any higher. We only have 10 digits. So we carry over from the 1's to the 10's and from the 10's to the next digit over, which will be the hundreds. And so we end up with 100. Okay, fair enough. Let's take a look at how this works in binary now. So in binary, we're going to start off with 0 plus 1 again, just as we did in decimal. 0 plus 1 in binary is equal to 1, just as 0 plus 1 in decimal is equal to 1. But as soon as we get to the next step, we run into a problem. What does 1 plus 1 equal in binary? Well, this is analogous to the situation we got to before when we tried to add 1 to 9 in the decimal number system. In the decimal number system, we had those 10 individual digits. In the binary number system, we only have 2 digits, 0 and 1. So when we add 1 to 1, there is no third digit. There's only 0 and 1. And so we need to go ahead and carry the 1 over. So this will actually give us 1, 0. We can go ahead and add 1 to 1, 0, which will give us 1, 1. When we try and add 1 to 1, 1, this is similar to the situation where we tried to add 1 to 99. We need to carry the 1 over, and so we're going to get 1, 0, 0. We can keep on going with this, so 1, 0, 0 plus 1 equals 101. We can keep going and continue on, and so what I've written up here is the first 8 numbers of the binary number system, or actually the first 9 if you consider 0 as the first number in the binary number system. So 0, 1, 1, 0, 1, 1, 1, 0, 0, 101, 1, 1, 0, 1, 1, 1, and finally 1, 0, 0, 0. So here are the first 16 numbers in the binary number system. And you can see that they are the equivalent of the decimal numbers 0 through 15. You'll also notice that I've got these little subscripts next to each of the numbers. So these subscripts are sometimes used to disambiguate when it's not clear what particular number system a number is using. So in this example here, I've got the number 6 on the left, but I want to emphasize that it's a decimal number. So that 10 in subscript after the 6 represents that 6 on the left side here is base 10. And the 2 on that's a subscript on the right represents that number on the right is base 2. Now, without that subscript 10 and without that subscript 2, you would probably guess that the number on the left is base 10 because it's clearly not binary. It's got a digit there, 6, which does not exist in the binary number system, although there are some other number systems like the base 8 number system, which occasionally gets used in computer science. And then there's a base 16 number system called hexadecimal, which does get used quite a bit in computer science. We'll look at that in another lecture. And so that 6 on the left could be either one of those number systems. And so putting that 10 down there at the bottom emphasizes that this is, in fact, a decimal number. And on the right, 110, this could represent 110 in base 10. And so that little subscript there, 2, tells us that, no, this is not 110. This is actually 110, which does kind of bring us to the next question, which is, how are we working out the equivalencies of these different numbers? So let's take a very short look at this. And I'm not going to require you guys to be able to do the conversion from binary to decimal, at any point in the quarter. And this is the point where I would normally say, we're not going to make you do it on an exam, but hey, because we're under quarantine, there are no exams. So go coronavirus, I guess. But I do want you to have a sense of how it works. So again, we're going to start with a decimal number because this is a system we're used to. And by reminding ourselves of how the system actually works will help us when we try and convert it to binary. So here I've got the number 1891. Now, if you think about what does 1891 actually represent, we've got 4 different digits here. The one on the far right represents 10 to the 0th power, which is our ones. The second number over, the 9, represents our 2 to the 1st power, or our tens. The 8 represents 10 to the 2nd power, or hundredths. And the 4th number over represents our 3rd powers, our 10 to the 3rd, which is 1,000. So if I'm looking at 1891, I know I have 1 10 to the 0th power, I have 9 10 to the 1st powers, 8 10 to the 2nd powers, and 1 10 to the 3rd power. So I have 1 plus 90 plus 800 plus 1,000, which gives us 1891. Let's go ahead and take a look at how this works with binary numbers. So here I've got the binary number 1101. What is the decimal equivalent of this? Well, on the far right, in the 0th place, I have my 2 to the 0th. So these are 1 because 2 to the 0 power is 1. The next place over represents my 2 to the 1st powers. So those represent our 2s. Next to that, to the left, I have our 2 to the 2nd powers, which represent 4s. And then one step over from that, I have our 2 to the 3rd powers, which are 8s. In this particular case, I have 1 2 to the 0th power. I have no 2 to the 1st powers. I have 1 2 to the 2nd power, and I have 1 2 to the 3rd power. So I have 1 plus 0 plus 4 plus 8, which means that this is the equivalent of a decimal 13. So one thing that's going to be important for us when we're representing information is how many different combinations can we store in a given number of bits. So let's start off with 1 bit. What can we represent in a single bit? Well, we can either represent a 0 or a 1. What is that actually good for? The most common thing that we can use a 0 or a 1 to represent is actually whether something is true or false. So are we going to be able to come back to Stanford for summer session? Well, if that bit is storing a 1, then the answer is yes. And if that bit is storing a 0, then the answer is no. How many different combinations can we store in 2 bits? Well, here are the different combinations in 2 bits, and you can see that there are 4 possible combinations. How about the combinations in 3 bits? Here are the different combinations in 3 bits. And then finally, here are the combinations in 4 bits. So the way to think of these is you can either think of them as, oh, those are binary numbers, and we saw how to convert those to decimal a minute ago. So, if we have these 16 possible combinations, these could represent the decimal numbers between 0 and 15, but they might be used to represent something else. So for example, I could use these 16 combinations to represent the 10 provinces in Canada. So if we were a school in Canada and we wanted to know which province somebody lived in, I could have 0000, for example, represent Prince Edward Island, and 0001 representing Nova Scotia, 0010 representing New Brunswick, and so on. Could we represent information about US states in our 4 bits? No, we can't. There's 50 different states, and we can only store up to 16 different combinations in our 4 bits. So while our Canadian provinces fit in the 4 bit, and in fact, we could comfortably add in the 3 Canadian territories as well, we simply do not have enough space in 4 bits to store the US states. And in fact, if we had 5 bits, we still couldn't store it. We're going to see that we actually need 6 bits to store all the states of the Union. So we've seen that in 1 bit, we can represent 2 combinations. In 2 bits, we can represent 4, 3, 8, 4, 16. And it turns out there's a simple formula here. If we have n bits, we can represent 2 to the n combinations. And so here you can see the number of combinations we can have for 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 bits. Now, when you're looking at these different combinations, keep in mind that these individual bits could represent numbers. They can represent positive and negative numbers. They can represent different things like our Canadian provinces. We could use a certain sequence of bits to represent dorms at Stanford. And so one of the things that the programmer is going to have to decide to do is what do they want to do with the individual bits. When we're designing a program, we're going to need to decide how many bits to set aside for what particular quantities and how we're going to represent things with bits and bytes. And that's something that we're going to be exploring more later this lecture and throughout the rest of this week. Now, another thing that you might notice is if we're looking at these numbers here, 2, 4, 8, 16, 32, 64, 128, 256, 512. These may look a little bit familiar to you. If you've gone shopping for a new, say, iPhone recently, how much memory do you buy in an iPhone? Can you buy 100 megabytes? Can you buy 250 megabytes? No, you buy 128 or 256 or 512. Why? Because those are powers of 2 and because internally the computer uses the binary number system. Now, we've only solved half the mystery, though. Now we understand why we buy iPhones with 64 or 128 or 256. But why do we buy them in megabytes or gigabytes instead of millions and billions? Well, it turns out that millions, billions, thousands, these are all powers of 10. And again, internally, we're using the binary number system, not the decimal number system. And so kilobytes, megabytes, gigabytes, and terabytes are the base 2 equivalent. And you can see from this table here that 2 to the 10th is about 1,000, but it's actually a little bit bigger. And 2 to the 20th, which is a megabyte, is about 1,000,000, but it's actually a little bit bigger. And the same thing for gigabytes and terabytes. So the idea here is we're going to give you roughly the same amount as 1 billion or 1,000,000 or 1,000. But we want to do it in a power of 2. And you can see here are some higher order numbers that you might run into someday: peta, exa, zeta, and iota. I should mention that there is some disagreement between the electrical engineers and the computer scientists on whether or not we should be using powers of 2. So there are places where when we're working with electrical engineers, they will use kilo, mega, or giga, and they'll actually be referring to thousands, millions, and billions in base 10. And so the most common place you might run into this is when you're talking about communication speeds. Those are generally actually given in powers of 10. All right, in the next lecture, we're going to take a look at what happens when things go wrong with our binary numbers.